everybody, I'm going to go over acetals in this video. So in class, we had seen an example of an acyclic acetal being formed. I'm going to go over the synthesis of a cyclic one. This is a really common acetal to make in terms of just using ethylene glycol as your alcohol source. It already has two alcohols. It forms this really nice ring-shaped acetal. And it's pretty common in that respect because ethylene glycol has a pretty high boiling point, which definitely helps when you're trying to do the various, remove water type things. You want to be able to have your alcohol have a boiling point that's higher than the water so that you don't lose your alcohols and you only lose your water. Okay, so the first step of the mechanism here is because we are in acid, and so keep in mind, I'm switching up the acid here. I've got para-toluene sulfonic acid. We saw this last semester. So para-toluene sulfonic acid is, write this out, para-toluene sulfonic acid. Okay, so the structure of it is this. We've got a benzene ring, a toluene, right? And then para-sulfonic acid. Okay, so this part, it's pretty much just sulfuric acid. It's just attached to an organic component so that it makes it soluble in organic solvents. So that's a pretty nice acid that's often used in these types of reactions. All right, so first step is we're going to protonate. I'm just going to cheat and bring this over here. Okay, so we're going to protonate our aldehyde. And then we're ready to have our first nucleophilic attack of our alcohol. So we're going to bring in our ethylene glycol here. So then we get to this positively charged intermediate. So we're kind of in that stage now where we're thinking about it like a tetrahedral intermediate. We're aiming to continuously be making carbonyls. In this case, we want to use water as our leading group. And if you're thinking about like, well, we could just go backwards and go like this, you're absolutely correct. And there is some component of that to this. But when we're drawing out these reversible reactions, it's important to keep in mind to keep focusing on the direction that's going to actually give you product and that's going to be productive, because you can definitely go down the rabbit hole in terms of some of the acid-base reactions that you can do that, yes, they probably do occur, but it's only the ones that are going to shake out into product that are the ones that we really care about. And we do have ways to kind of shove them that direction by doing things like removing water in the process. So we're going to go ahead and deprotonate here. So I'm just going to use another equivalent of ethylene glycol to do that. You're going to have a lot of this, of whatever alcohol you're using around. So it's never a bad one to use whatever alcohol or amine that you have as a base for any of the acetal or the amine-enamine reactions. So we can go ahead and deprotonate that positively charged oxygen. That's going to get us to a neutral intermediate. And we've also formed some protonated ethylene glycol. Okay, so we have our protonated ethylene glycol. Now we're going to use that to protonate our alcohol to make water for our leading group. So we're going to go ahead and protonate that. Okay, so now we are ready. Now that we've got our leaving group situated, we've got lone pairs over here that we can use. So we can go ahead and reform that carbonyl, kick off our leaving group, very similar to the tetrahedral intermediates that we did when we were doing the Grignard reactions and all that. And we're back to another really good electrophile. Okay, so it might be tempting to do what we did in class and to bring in another equivalent of ethylene glycol to do this type of move again, but it's actually going to take longer for one of the ethylene glycol molecules, got the word, to come in rather than use this alcohol that's already present in the molecule, okay? Especially because this is forming a 5-membered ring. Those form really, really fast. So it's gonna be way faster to do this intramolecularly rather than doing it intermolecularly. So we're gonna go in the same molecule. That's gonna form our 5-membered ring. We still have an H on that. So the last thing is we just need to go ahead and deprotonate that. Again, we can use ethylene glycol for this. And it can just go on that conjugate acid, and it can go ahead and start doing this process again with another molecule of aldehyde. Okay, so we can go ahead, keep being more acid. And so this is catalytic in the acid. So you really don't need a lot because you just need to have one little proton source around to kind of do the whole thing for you. Okay, and then we also have water present as well, right? So the water that we're creating, that's what we are removing from the reaction using a Dean star trap or some other adsorbent to help kind of trap that water away. And that's going to help us drive the equilibrium to that acetal. So let's say that we did our reaction with the acetal and then we were done with it and we want it to get back to the aldehyde or the ketone that we started with. So that's going to be a hydrolysis reaction. So I'm going to take the same one. So if I'm trying to lean the equilibrium towards ketone or aldehyde, that means I need to be adding water so that I have more water over here to get to starting material for my equilibrium to lean that way. So I'm going to add water and acid. Okay, I'm just going to use HCl this time. It's a good kind of aqueous acid, so it's going to work out fine. And then we're going to go ahead and do our mechanism. So the important thing to keep in mind here with these mechanisms is that you can literally draw out the formation of the acetal, and you'll see that all of these intermediates that we draw here are going to be identical to the intermediates that we're going to draw for this hydrolysis reaction. Okay, so first step, we're going to protonate because we are still in acid, so that's still going to be the first thing that we should think about doing. Okay, so now we are ready to have that leave. So we're back to our tetrahedral intermediate situation where we can form a carbonyl, kick off that leaving group. Okay, which you can kind of see I'm pretty much already, I'm right here right now. So I'm spot on in terms of going that direction. So now I've got a really good electrophile. So I'm in a good place for water to attack at this point. Another reason why we need a lot of water around right now. Okay, so I have my protonated intermediate now. We can go ahead and use water to deprotonate that. Okay, so then we know that we're trying to get this to leave, so we're going to protonate that. I'm going to use H3O plus because I just made that in the previous step. Okay, so now I'm again at that tetrahedral intermediate stage where I'm ready to make another carbonyl. So I can reform my carbonyl, kick off my leaving group, and that's going to leave me with a protonated aldehyde plus my alcohol. Okay, so I've got my ethylene glycol back. Then we can do a final deprotonation with our water. Get back to our benzaldehyde. We've reformed our acid catalysts, and we've gotten our ethylene glycol back. Okay, so that's what the hydrolysis looks like. Once you're done, you can just throw in acid and water, and then you get right back to your aldehyde or ketone that you started with. So let's look at an example of when this might be helpful. I'm going to make this a little bit bigger. Okay, so this synthesis, if we're trying to make this particular compound, so it's pretty clear that they're setting us up for some type of Grignard reaction between this bromine and that ketone, but we definitely have a problem when we have a bromine and an aldehyde or some sort of electrophile in the same molecule. So that means that this could just attack here. It could also, while you're making your Grignard, it could attack another aldehyde and give you a huge, like just a humongous mess. So what we need to do if we still want to have this aldehyde intact, we just need to protect it so that it won't be seen or detected by the Grignard reagent. So a good way to do that is to make it into an acetal. So if we just add in our ethylene glycol here and some sort of acid, and I'm fine if you just write like catalytic H3O plus, that's fine. And then we can make a little note that we want to remove water here so that we force that equilibrium to the acetal. Then we can make our acetal right here. Grignard is going to look at that and not think anything at all. It's just going to move right on by. So now we're ready to turn this into a Grignard by adding in our magnesium. Okay, and we're going to have absolutely no issues with this. Then we can go ahead and add in our cyclopentanone. Okay, so we add that in, that's going to do our Grignard reaction. And then if we follow that up with H3O plus and water, so that's going to do two things actually. If we have, we'll change it to HCl. So if we have a strong enough acid, then we're certainly going to deprotect this as well as quench our Grignard, okay, and our O minus. So that's going to do kind of two things. Actually, we're going to do just one step at a time here so that we can see what's really happening. All right, so we're going to have this attack here, move up. I guess I'll tilt it the way that we have it drawn out here. 1, 2, 3, 4. 1, 2. Okay, so then we get to this acetal and O minus, and then we can just finish that up with HCl, H2O, and that is going to protonate this and deprotect that to get us back to our aldehyde and our OH. Okay, so really, really handy to use acetals as protecting groups here. So as always, let me know if you have any questions, and I will see you all later.